So we talked a little bit about the history of the periodic table, and if you talk to some scientists, probably mostly chemists, but they will say that this was actually the greatest advancement of modern science. And though I can agree, probably the greatest one for chemistry, you're never going to get scientists to agree on anything like that altogether, but this was a pretty significant task. Now, Mendeleev was a person who was slated as a creator of the table. And this was if you look, Mendeleev 1904, you have these different things arranged in group one, group two, group three, group four. Now, what he did was the idea was that he believed, or the rumors that he was, and this wasn't back in 1904, but it was, the idea that he used the game solitaire, where you have ascending patterns, but there's an order to how the patterns are arranged. So, one thing that I want you to look at is if you notice the crosses or the X's is spots that weren't entirely correct, but the filled in dots were the ones that he actually got correct. But if you also notice, there are gaps with these. So before playing the video, I want you to go to the worksheet. What do you think that these gaps could actually represent? Okay, so now that you thought about it a little bit, and it's like late 1800s, 1816 or something like that is when Mendeleev actually created the periodic table, first published it rather. So what those gaps represent are elements that weren't discovered yet. So what Mendeleev did was he took the different properties of all the materials and elements that they knew that time. So they knew roughly the size, they knew the boiling point, they knew the melting points, they knew what it reacted with. So if you think back to Isle, these were a lot of the observations Mendeleev was able to, look at and use, and then his model was the periodic table. So what would his testing experiment be? Well, those gaps represent elements that Mendeleev knew that there had to be other elements yet they just weren't discovered. So what he was able to do is he was actually able to predict the size of the elements, the atomic mass, and what those properties would be before those elements were ever discovered. And shortly after he published his paper, a few years later, one of those elements was actually discovered. And the interesting part was that the properties of that element were pretty much identical to what Mendeleev would have predicted that element would have been like. So, as a result, you can see that, his model, this is what was helped to show like there's some credibility to his model with this. So when we're going down and looking at these different groups, when you look at a picture of modern day periodic table, you have group one, group two, group three, four, blah, 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 blah. Well, the reason these patterns are similar is that there's the outer shell of electrons and how they react. So they have certain um, properties with them, or what we call trends. So group one we call the alkali. So early in human history, people noticed that when you mix these water to form a solution, it was kind of useful for removing grease, described as being alkaline from the Arabic word alkaline meaning ashes. So you can look at the alkaline metals. I included the link in the other worksheet. We're not going to watch it here, but you can kind of watch that there. Group two form alkaline solution. These were the earth elements. They don't change when placed in fire, so we know that they're alkaline earth. Group 17 were known as the halogens. This comes from the Greek word meaning salt forming. Many of these elements are forming salt. And then group 18 were the noble gases. They don't interact. So if you think of the nobles, the kings, the queens, they were above everyone else, so they never interacted with peasants or common folks or anything like that. So looking at atoms, we kind of have a little bit of a description about more information about them. Well, most of the atoms actually date back to the Big Bang. This is when everything was compressed in one big explosion and all the galactic guts got spewed everywhere. In a universal standpoint, 90% of the atoms in the universe are actually hydrogen atoms, so a proton with an electron. Helium is the most next abundant. It's about like 8%, and these are typically formed in stars. Anything heavier than that is where we get the extreme explosions due to pressure, gravity, and explosions and all that fun stuff. And like we said, these atoms are consistently moving. They're always bumping into things, going back and forth, but also these atoms are incredibly ancient. So, you might have heard somewhere like, oh, you're breathing in the air that the dinosaurs breathe in. Well, actually, that's true. You do breathe in atoms that you breathe in have been around since the origin of time. So you're breathing in air that the dinosaurs breathe in, or Columbus, or King Tut, or whoever you want to mention. You're sharing these air because every time you exhale a breath, there's about 10 billion trillion atoms within that. So kind of want to review a little bit about it. We talked a little bit about electrostatics, but I also kind of want to just go over some of the stuff. If you look at the fundamental parts of an atom, the nucleus is where the protons and neutrons are, with the exception of hydrogen, where a hydrogen atom has just a proton and just an electron. Now, protons have mass, electrons actually have mass, so it's incredibly small. Well, protons have an incredibly small mass as well, too. It's like 1.6 times 10 to the negative 27th kilograms. But it would take about 1,800 electrons to equal the mass of one proton. So even though there's a great mass difference, the size of the charges are opposite, but the magnitudes are the same. A neutron is about the same size as a proton, but it's neutral, so it has no charge. It is a little bit more massive, but for our intents and purposes, it's the same. Now, again, size matters. We talked about scale, and we talked about scale in astronomy, but looking at scale here with chemistry, this is another issue where now we're looking at the really, really small level. A proton itself has a radius of about 0.87 times 10 to the negative 15th meters. If we were to look at the proton where the size of a 1 meter ball, and so that's the proton, how big would the hydrogen atom be? So the question is really asking is that first electron, which in hydrogen only has one electron, where would that electron be located? So these are your choices. Is it 1,000 meters, 20,000 meters, 60,000 meters, 100,000 meters, or 150,000 meters? Think about it for a second. Which one do you think the answer is, and put it in the worksheet? So, well, let's see. Your answer is actually about 60,000 meters. So that electron would be located 37 miles away. So to kind of give you an idea, that's a lot of space. And, you might have read somewhere it's like, yeah, 99.999 whatever percent of everything is actually nothing. And that's kind of actually true. Most atoms are empty space. So everything that makes up you and me, all the atoms that make up me on an atomic level, it's mostly nothing. There's mostly space in between the nucleus and the electrons. Well, why doesn't everything fall apart? Well, on an atomic scale, atoms never touch. Protons never touch another proton. Electrons never touch another electron. So we have all this empty space, but we have these electric fields. And so on an atomic level, it's these electric fields that push and pull back away from each other. So this is how things push or pull. It's never actually a physical contact, but it's an it's a microscopic one. It's all due to these electric fields. So I want you to think about that for a second. And here's a question. So remember if you were a little kid, maybe not so little, not so long ago for some of you, and you would get into fights with your sibling. You might hear your mother, father, some other parent, or whoever, older sibling, whoever, they yell in the room, "Don't hit your brother!" Or "Stop it, stop touching each other. Stop touching me." So actually, if you knew what you knew now, and go back in time, what could you actually say at that instant to your parent or sibling, whoever that's telling you that, and actually be correct? Think about it for a second. Okay, so put your answer in the worksheet. So how do we identify the elements? Well, we look at them basically by the atomic number. So if you see like here, potassium, again, you have the 19 and 39 on top. Well, that atomic number is what's on top. Now, the way I used to remember it between atomic mass and atomic number, the number is north goes up towards the top. That number tells you how many protons there are in that particular element. So if it has 19 protons, it is potassium. The number on the bottom, which is always going to be bigger, it's protons plus neutrons, which a proton and neutron we call a nucleon. So we're going to round at 39.098 to 39. So 39 minus 19, we know we have 19 protons, which means we have to have 20 neutrons. So again, a proton neutron, we measure it in atomic mass unit because again, a proton is 1.66 times 10 to the negative 27th kilograms. We're not going to go around using that number all the time. So which one has more neutrons, cobalt or nickel? Think about it for a second. If you said cobalt, you're right, because cobalt on the bottom, that 58.933, it rounds up to 59, so 59 minus 27 is 32. Nickel, that 58.693 rounds up to 59 as well, but 59 minus 28 is 21. Now, what do you notice about these three? Well, they're all Fe, which means they're all iron. The atomic number is all the same, 26, 26, 26, that's all good. But if you look at the bottom, the 56, 57, 58, that's your atomic mass. Those are all different. So what has to be similar? What has to be the same? Well, they all have the same number of protons, so they all have to be iron, but they all have a different number of neutrons. This is what makes them different, and this is what we call an isotope. These are all isotopes of iron. If I go back to that periodic table here, one of the titles up here was isotopes. So if I click on, let's say, iron, it has a 7 here. That means there's 7 different isotopes of iron. And we call them by the atomic mass. So this is iron 60, iron 59, iron 58, iron 57, iron 56. So here, iron 56, 57, and 58. Now, once we have these elements, we start looking at how do they react, what do they do? And this is what we call properties. And properties come in 2 different types. The first is called physical property. This is how it looks, how it feels, the color, the hardness, the density. So this is how we describe it as itself. Now, physical properties also come with physical changes. I could do something to materials. I could rip it up. I could freeze it. I could tear it. A physical change is one in which I'm altering that physical property, but not the actual substance. It's still that thing. So if I rip up a piece of paper, it's still paper. I didn't change it into something else. If I take a block of wood and I chop it in half, it's still wood. Now these changes are typically reversible, not always, and this was a big misconception that we have sometimes with science. We think that the other type of changes are like, oh, if it is a reversible, it has to be a physical change. Not always. Now, chemical is our second type of property. This is how one material will react to something else. So if I go back to this property, let's click on magnesium, and I go back up here to properties, melting point, boiling point, electronegativity, valence, the hardness, density. These are all different properties of magnesium. So chemical changes, a chemical property is, so for example, metals rust, copper turns green, baking soda and vinegar produce water. This is how these react with other elements. A chemical change is a change in which I have a brand new substance. The actual elements or the molecules, the atoms that make up that substance are changed. They're different. The properties are new. I have something new. I have something different. If I burn a piece of paper, well, technically it's no longer paper. And that process we typically call, where new materials are formed, we call that a reaction. So the way that they're arranged in the periodic table shows how they kind of behave. So all of these substances, just like in the groups we learned about before, they all have these same properties. That's how Mendeleev was able to arrange them in a certain way, because they looked at the properties of these things. We can also break up these into larger groups: metals, metalloids, and nonmetals. Metals make up most of the elements, which are 88 of them. So if we look at here, all along here, these are metals. These are shiny, opaque, they're good conductors, high density, malleable, and ductile. Malleable means I can bend it into different shapes. Ductile means I can draw it onto long, thin wires. They easily lose electrons and they corrode easily. So I'm going to stop it right here because we're about out of time, and we're going to do the next video.